We are live.
Okay. Well, dear colleagues, it seems that there are 37 of you who are here instead of thinking about going for a walk in sunny Brussels Friday afternoon. And the good news is that first we announced a non-seminar with a non-speaker about a very interesting issue about perceptions of reality. And space-time, and how we deal with our cognition on that. But actually, Donald Hoffman is with us from Irvine, California. Fortunately, missing a link in a time zone is less irreversible than missing a plane from California to Brussels. So let's see the positive side of our virtual reality, even if this virtual reality sometimes is extremely tiring. And I'm sure that we are all part of some reflection of Professor Hoffman on how our cognitive abilities are developing or underdeveloping in this context. So I already introduced Professor Hoffman, being Professor Emeritus of Cognitive Science at the University of California and author of so many articles and books that we cannot summarize apart from highlighting the case against reality, why evolution hid the truth from our eyes. So Donald, without further ado, I let you get started with this very exciting seminar. Thank you for being with us in spite of the mismatch and the little confusion about time zones and different realities. Thank you.
Oh, my pleasure, and thank you again so much for inviting me. This is a great honor. I'll pull up my screen here. Let's see. There we go. Does that work?
Perfect. Yes. Thank you. We see very.
Okay. So I'll talk a little bit about what I call conscious realism. So when you look at your face in the mirror, all you see is skin, hair, and eyes. But what you know firsthand that you can't see in the mirror is the rich world of your conscious experiences, your hopes, your dreams, your aspirations, your love of music, the colors and shapes and sounds that you experience. So we know that what we see literally is just skin deep, but that there's a whole world of conscious experiences that we know firsthand that's far richer than what we can see. When I look at my cat, I believe I'm interacting with an entity that has lots of conscious experiences, but I have less insight into those conscious experiences. With a mouse, perhaps even less insight. By the time we get down to bacteria, we have very little insight, if any. We even doubt whether we might be interacting with the consciousness. And by the time we get down to rocks, we're pretty convinced that what we're dealing with is not only not conscious, it's inanimate. And so we just assume that there's no consciousness to be thought of there at all, although we can talk about panpsychism a little bit later. And then in the case of artificial intelligence, we begin to wonder, could there be AIs that are conscious? One argument could be that the human brain is a machine, it's a carbon-based machine, and somehow it gives rise to consciousness. So perhaps there's nothing special about carbon. And at some point with silicon, we might get it complicated enough, the right kind of dynamics, that even AIs could be conscious. And most of our thoughts on this topic are in the framework of a physicalist view of reality. So in that view, 13.8 billion years ago, roughly, the universe began with the Big Bang, and it was just space-time and matter and energy, no life, and certainly no consciousness. And that didn't come until, hundreds of millions, perhaps billions of years later, that there was life. And then who knows how much later consciousness came onto the scene. And so that's the standard physicalist framework in which we, as scientists, have thought about this problem of consciousness and its relationship to the physical world. And from that point of view, space-time and matter are the fundamental entities, and as scientists, we have to give a theory about how consciousness emerges from the right, perhaps complex interactions of matter. So that's the standard framework. And it's a physicalist framework. It's also a reductionist framework in the sense that in this point of view, there are um, the the smaller the scale that you go into, the finer and finer resolution you go into, in some sense, you're getting to better and deeper principles. Right now, the deepest principles we have are the standard model of physics. These are some of the particles that are there in the standard model of physics. And so once we know these particles and their properties and their laws of behavior, we can then boot up chemistry. From that, we can boot up biology. From that, we can boot up neuroscience. And that from that, perhaps we can boot up the theory of consciousness. So it's a reductionist framework in which as you go to finer and finer scales, you get to deeper and deeper principles from which everything else emerges. And that's the framework in which most of the work in consciousness is being done right now. And as we go up in the scales, we eventually expect to understand how the fundamental principles of physics lead to chemistry, but then to pyramidal neurons and their behaviors, and ultimately to the brain and its systems, a level approach to the brain, systems neuroscience approach to the brain, and then eventually uh, the hope is that from that we will see how brain activity gives rise to conscious experiences. And that's the framework in which most of the research is being done. I think of, for example, the global workspace theory of consciousness, and in which is sort of the broadcast architecture of the brain that somehow, or computing system that somehow gives rise to consciousness, or integrated information theory, in which having the right causal computational structure with the right amount of integrated information will give rise to consciousness. Or Penrose and Hameroff's theory, in which coherent, coordinated collapse of microtubule quantum states somehow gives rise to conscious experiences. In each case, the main theories in this arena assume physicalist framework, reductionist framework, and assume that consciousness emerges somehow from the right physical activity. That's the framework that's been the fundamental framework for consciousness studies for many decades. And as Searle, professor at UC Berkeley, has put it, the brain is a machine. It's a conscious machine. So, of course, some machines can think and be conscious. Your brain and mine, for example. So the idea is we start with physical machines, and when we get the right kind of machines, consciousness will emerge. And that includes, again, artificial intelligence, consciousness, once we figure out the right principles. And as David Chalmers put it, implementing the right computation suffices for rich conscious experience like our own. So in some sense, consciousness is nothing but the right computations, the right algorithms in the right kind of hardware. That's what our experiences are. And that seems like a reasonable framework. It certainly fits in with a successful scientific framework of physicalism and reductionism that's put us in good stead for 400 years and has done an incredible amount of great work, or it's informed an incredible amount. So, and eventually, what we would hope from this framework is that once we understand the brain processes that are responsible for our conscious experiences and our minds, then we can effectively download them. We can understand the program that is our mind, that is our consciousness. We can download it, and we could put it into computers. So when we come to something as impressive as the experience of color, just to take a specific conscious experience, we know that there are strong correlations between neural activity and the experience of color conscious experiences. So there are many areas of the brain that are involved in color perception, from, of course, the cones in the eye to various cells in V1, but there's an area called V4 that seems to be correlated with our conscious color experiences. And you have a V4 in both the left and right hemisphere. And remarkably, if you have a stroke in area V4 in the left hemisphere of the brain, you get what's known as hemiachromatopsia. Whoops, hemiachromatopsia. So here, everything on the right of where you're looking is in shades of gray, and everything to the left of where you're looking is in full color. And we can also do this with transcranial magnetic stimulation. If we take a TMS device with a normal person and just touch it to the skull in the area of before and put it in inhibit mode, then we can temporarily induce this hemiachromatopsia. And then when we turn the magnet off, the color comes flowing back in. You literally experience the color flowing into your visual world. And so here's a case where we have, it seems, high confidence that brain activity is causing the conscious experience because we're intervening, right? I literally can take a magnet, intervene to interfere with the brain activity, and the conscious experience of color disappears. So that would seem to indicate some kind of correlation. And of course, correlation doesn't imply causation, right? The rooster crow is correlated with the sunrise, and indeed the rooster crow often precedes the sunrise, but none of us thinks that the mere fact that it precedes the sunrise entails that the rooster crow causes the sunrise. And so there is an open question about, does brain activity literally cause our conscious experiences? And of course, as I mentioned, we tend to think that it does because there seems to be more than just correlation. There is this intervention that we can do. I can literally intervene with the brain activity and get corresponding changes in the conscious experience. And so that tends to make us believe that we're beyond the correlation causation problem, that we can intervene. So, but despite this fabulous framework of physicalism, reductionism, and the ability to manipulate brain activity and see changes in conscious experience, and despite the theories that I just mentioned a few minutes ago about consciousness and brain activity, we still are in a position where we think of this as the hard problem of consciousness. We don't feel like we've really gotten a handle on the hard problem of consciousness. How does brain activity or physical activity more generally cause our conscious experiences? It's still remarkably a mystery, and it's not for lack of brilliant people, many of them my friends, who have been working very, very hard on this. But the fact is that none of the theories that I have mentioned, the integrated information theory, the global neuronal workspace theory, the microtubule collapse, or orchestrated collapse of microtubules theory, none of these theories can explain even one specific conscious experience. And I want to pause on that. This is an important point. If you ask the authors of these theories, great. Say integrated information theory. What is the causal computational architecture with the right integrated information that is, say, the taste of vanilla or the smell of a rose? I would like a scientific theory that starts with your mechanism or your global neuronal workspace or whatever it might be, and predicts precisely the experience that should happen, and explains why this particular, for example, orchestrated collapse of microtubules must be the taste of chocolate. It could not be the smell of vanilla, and explain exactly why that is the case, or that this particular causal computational architecture must be, a headache, and it couldn't possibly be the feeling of velvet. And these are my friends. I've asked them, Stuart Hameroff and Giulio Tononi, can you explain even one specific conscious experience? And the remarkable thing is that these theories cannot yet explain even one specific conscious experience. So the state of play in our understanding of models of consciousness is that we have these theories, but here, at least until now, we can't explain even one specific conscious experience and its genesis this way. So I've mentioned global workspace, integrated information, neuronal microtubules. One other approach to this that Keith Frankish and Dan Dennett are famous for is to say, well, there is no such thing as conscious experience. So we're barking up the wrong tree. We have an illusion of conscious experience, and it's an evolution has shaped us with this illusion for reasons that we can go into. But there again, you don't really escape this problem because, as I mentioned to Keith in our discussions on this, we now have to explain the brain mechanisms that are responsible for specific illusions. So what is the brain mechanism or the brain activity that's responsible for the illusion that I'm having a taste of chocolate? And why is it that that brain mechanism must correspond to the illusion of the taste of chocolate, and it could not possibly be the illusion of the smell of vanilla? So just calling it an illusion doesn't get rid of this problem of we need scientific theories, not just general theories about how consciousness might generally work. We need scientific theories that say this pattern of brain activity or this physical activity must be the taste of chocolate or the illusion of the taste of chocolate, and it could not be the smell of a rose or the illusion of the smell of the rose. So it's important just to see where we are in the state of play. We can't explain one specific conscious experience. So, as I said, the taste of chocolate. There's no theory that can explain the taste of chocolate or the smell of a rose or the sound of a saxophone. So what's going on here, right? It's now one thing that may be going on here is well, this is a hard problem, and we'll need more decades to study neuroscience and systems neuroscience, and we just will need that experiment, that breakthrough, that we all go, oh, that's how it works. Why didn't I think of that? And we'll solve the problem. So that's one possibility, and I think that is the hope that's driving a lot of work in the field right now. Is that it's until we discovered the double helix structure of DNA, life was a bit of a mystery. But once we saw, A, C, G, and T, and we saw the double helix, we go, oh, hit ourselves in the head and go, oh, okay, well, that's how it works. Of course, why didn't we think of that before? And of course, Schrodinger did in his What is Life book. He sort of hinted at it. But so we're looking for that, double helix moment in neuroscience that will break open the hard problem of consciousness. So that's certainly possible, and I think that most of my esteemed colleagues are hoping that and working toward that end, and I wish them well. But there's another possibility, and the possibility is that maybe we're making some deeply held assumptions that are deeply wrong. And maybe we should go back and reconsider some of our assumptions. And so that's what I've been doing, partly with the attitude that if 99% of us are taking a physicalist framework and we're having trouble so far in getting a solution, maybe at least 1% of us should go somewhere else and look for other hypotheses. So it's a matter of search strategy, right? So why put all of our eggs in one basket? So I've been searching around saying, okay, frankly, I've not been able to come up with any smart ideas from a physicalist framework, and my brilliant friends have good ideas but haven't been able to solve any problems. So let me look somewhere else. So I'm going to go back to our very fundamental assumption that space-time is fundamental, and I want to argue on evolutionary grounds and on grounds of physics, namely bringing Einstein's theory of gravity together with quantum field theory. I want to argue that the three main pillars of modern science, evolution by natural selection, quantum field theory, and gravity, all are telling us that space-time is not fundamental. That's the big move here. The science for the last, since Galileo has been about what happens in space and time. That's what science has pretty much been about. And it's been an incredibly powerful framework, and reductionism, the idea of going to smaller and smaller scales, leads to deeper and more fundamental principles. That has worked spectacularly. But our best theories are now telling us that that framework itself is a problem, and we need to move to a different framework. So the way it's put by some physicists is space-time is doomed. So in particular, Nima Arkani Hamed, for example, at the Institute for Advanced Study at Princeton, David Gross, who won the Nobel Prize for some work in string theory, Ed Witten, a Fields medalist, also at the Institute for Advanced Study at Princeton, working on physics, and many others have principled reasons within physics for saying that space-time is doomed. And I also want to give principled reasons for saying that from evolution by natural selection. So, but let me just first give what the physicists are saying. The argument goes like this. Quantum theory forces us to think not only about the systems that are being observed, but also the apparatus that we use to observe them. If I want to measure, say, the magnetic moment of the electron, well, I want to measure it to a certain amount of precision, well, I'm going to have more and more degrees of freedom in my apparatus if I want to get more and more precision in my measurement of the magnetic moment of the electron. And so imagine some fixed size room that I'm going to do this experiment in. It could be a very, very large room. It could be, a square mile or something like that. Or it could be the size of a galaxy, whatever fixed size room you want. And I want to measure the magnetic moment of the electron to, hundreds or thousands of decimal places. Well, to do that, I'll need to have more and more degrees of freedom in my apparatus because it's also a quantum system subject to the Heisenberg uncertainty principle. And as I have more and more degrees of freedom, the mass of that apparatus is getting larger and larger. And at some point, when I demand even more precision, the mass will be so large that gravity now, changes mass into curvature of space-time, and the whole room collapses into a black hole. And you destroy the whole experiment that you're trying to do. And what physicists will point out is that this is not just going to small scales that you have problems. Any macroscopic size room is going to have this problem that there are what they call no local observables. You can only measure things to a certain level of precision, and after that you create a black hole, and the whole experiment stops. So in our kind of space-time, de Sitter space, there are no local observables. That means that space-time itself is just an approximate concept. We saw this in the transition from classical physics to quantum. In classical physics, we could measure position and momentum in principle as much as we wanted. But in quantum physics, we learned that no, it's not position and momentum, it's position or momentum. You get one or the other. And it's that fact that you can't get precision in position and momentum at the same time that led to the whole conceptual revolution of quantum theory. And now they're saying an equally big or perhaps bigger conceptual revolution is needed now, because it's not just position or momentum that's the problem, it's space-time itself that is the approximate concept that needs to be revised. So space-time itself must emerge from something deeper. And by the way, they're making good strides toward finding that. I should just mention that Nima Arkani Hamed and many of his collaborators, there's many of them, are finding structures beyond space-time, things like they call the amplituhedron, spacehedron, associahedron, and cosmological polytopes. These structures have no Hilbert spaces, so there's no quantum theory. They have no notion of locality or unitarity, so there's no space-time. And yet, they are able to predict precisely the scattering amplitudes for particles at the Large Hadron Collider, like 2 gluons coming in and 5 gluons spraying out. These structures outside of space-time, with no quantum, no Hilbert space, no quantum theory in them, predict precisely these scattering amplitudes. And what's interesting is what makes the physicists excited about it is two things. First, these structures show that there are symmetries that cannot be captured in space-time, but that are true of the scattering events. Dual conformal symmetry and an infinite Yangian symmetry are among the symmetries that they're finding. So there are symmetries in the data that cannot be expressed in space-time, but are being captured by these structures behind space-time. And second, when you let go of space-time, the mathematics becomes easier. When you use so-called Feynman diagrams to compute 2 gluons in and 5 gluons out, it's hundreds of pages of algebra, because you're trying to force all the processes to be done, virtual particles in space and time. When you let go of that, what's hundreds of pages of algebra in space-time turns out to be 3 or 4 terms that you can compute by hand on a piece of paper, in this deeper framework. So when you let go of space-time, the physicists are finding you see deeper symmetries that are true of nature but can't be seen in space-time, and the math becomes easy, and it's ugly in space-time. So that's why they're quite excited. The younger generation is quite excited. Space-time has had a great run for 4 centuries, but it's over. It's now time to find what's behind space-time and how space-time emerges from this deeper structure. So the bottom line is, in practical terms, space-time is doomed because you can't make precise measurements. The very act of trying to make a precise measurement creates a black hole and destroys the very thing you're trying to observe. That's the argument from physics. I'll just mention the argument from evolution now. Most of us think that intuitively there are good evolutionary reasons to think that our sensory systems tell us truths about objective reality. The argument goes like this: those of our ancestors who saw reality more accurately had a competitive advantage compared to those who saw less accurately in the daily functions of life that are important, like feeding, fighting, fleeing, and mating. And so those who saw more accurately were more likely to pass on their genes that coded for the more accurate perceptions. And so after thousands of generations of that, we can be quite confident that we are the offspring of those who in each generation saw more accurately. And so we can be confident that in the normal case, we see reality pretty much as it is. Now, of course, not all of reality. No one thinks that we see all of objective reality, but we see those aspects of reality that are critical to us in our niche for our survival. So that's the standard argument. And then, put that way, it seems almost unassailable. What could be wrong with that kind of argument? But I decided about 12, 13 years ago to look at this more carefully. I mean, the argument is persuasive, but it's not a mathematical proof. And it turns out in the case of evolution by natural selection, John Maynard Smith back in the 1970s turned that theory into a mathematically precise theory. So we can actually run simulations and prove theorems. So we don't have to wave our hands about what evolution by natural selection will do. We can actually run simulations and prove theorems. And so I first ran with some graduate students, 2008, 2009, hundreds of thousands of simulations of organisms competing for resources, and we let some of them see reality, and others we didn't let see reality at all, and we wanted to see which were more fit. And we got evidence that the ones that saw reality as it is could never outcompete organisms, artificial organisms, that we didn't allow to see reality at all and just let them be tuned to the fitness payoffs. And of course, simulations are just simulations. They're not proofs. Maybe we got the wrong environments. Maybe we had some parameters that were artificial. So I then went to a mathematician, Chetan Prakash, and I said, I think we can actually answer this question, Chetan, using evolutionary game theory. Does natural selection actually favor veridical perceptions? And so Chetan and I worked on it, but Chetan's the mathematician, and we proved that veridical perception goes extinct. So the theorem is this: the probability is 0 that natural selection will shape any sensory system of any organism to track or present any true structures of objective reality. In other words, the probability of any kind of veridical perception of world structure is 0 for any sensory system of any organism. So that's just a theorem of natural selection, and we can go into that, if you want. But what this means intuitively is that evolution didn't shape our senses to be a window on the world, a window on truth. Instead, it shaped our sensory systems to be more like a virtual reality that guides adaptive behavior, but hides the truth. So it's dumbing things down, it's simplifying. So it hides reality and just gives us the eye candy that we need to behave adaptively. So if I'm playing, for example, a virtual reality game of say Grand Theft Auto, what I'm really doing in this particular example, this metaphor, I'm really toggling voltages and magnetic fields and some complex circuits and some supercomputer. But I don't see that, and I'm not aware of that, and I might not even have any knowledge of voltages and magnetic fields and supercomputers. All I see is, for example, a steering wheel. And I know that if I turn the steering wheel to the left, my car will go to the left. And if I intervene and turn my steering wheel to the right, my car will seem to go to the right. So I have this nice, useful fiction of causality, right? I can intervene on the steering wheel, and when I intervene on the steering wheel, I seem to have causal control, and it seems like the steering wheel itself has causal capabilities. But in fact, of course, the steering wheel doesn't even exist when I don't look. So I look in one direction, I see a steering wheel. I turn my headset to the right, I'm no longer creating a steering wheel. I'm now, say, looking at a red Ferrari now, and I'm rendering that. So the idea then is that space-time is not the fundamental reality. It's a data structure. Evolution by natural selection has shaped our species with a particular data structure, not to show the truth, but to provide us with a user interface, to hide objective reality and simply guide adaptive action. So the point is that evolution shapes the senses to guide adaptive action, full stop. Nothing about truth. In fact, the way to guide adaptive action is to hide the truth completely and give you simple eye candy that lets you control the truth without knowing what you're doing. When I turn the steering wheel, I'm literally in the game manipulating and toggling millions of voltages per second. That's what I'm doing in that metaphor, literally. But I have no idea. All I'm doing is just turning a steering wheel. So what I do is simple in terms of my perceptions. What I'm doing in reality could be arbitrarily complicated. And that's what evolution has done for us. It's given us a user interface that hides the truth completely and simply guides adaptive action. Or another way to think of it is like the desktop on your computer. If you're writing an email and the icon for your email is blue and rectangular in the lower right corner of your screen, that doesn't mean that the email in your computer is blue and rectangular and in the lower right corner of your computer. Anybody who thought that just completely misunderstands the point of the desktop interface. It's not there to show you the truth, the diodes and resistors and voltages. It's there to hide the truth. But of course, you have to take your icons seriously. You don't take them literally. My file is not blue and rectangular, but I have to take it seriously. If I drag that icon to the trash can, I could lose all my work. So we must take our icons seriously. They're there, shaped by evolution to keep us alive, but that doesn't allow us to take them, or doesn't entitle us to take them literally. And so that's why I wouldn't step in front of a train. Not because I take the train literally. No, it's just an icon, but I do take it seriously. And similarly, if I see a snake, I'm not going to pick it up. If I see a cliff, I'm not going to step off. Evolution gave us symbols designed to keep us alive. We have to take them seriously. But it's a logical error to conclude that we can therefore take them literally. It's a logical error that's built into us at about 4 months of age. Developmental psychologists tell us that at about 4 months of age, we get object permanence. We don't come to our belief in the existence of physical objects when we're not observing them through rational argument. We come to it through a process where we don't have informed consent. At 4 months of age, evolution by natural selection forces us to have this belief. It's like being baptized into the church at 4 months of age. Well, yeah, you're baptized in, but you don't have informed consent. And so this is our chance to check our assumptions. We're programmed to believe it, but and it's a very, very strong programming, but it's not true. So from that point of view, how do we go back to this problem of consciousness and the hard problem? What I'm proposing is the reason why the hard problem has been so hard for so long, and by the way, I should say for so long, Leibniz understood this. In the 1700s, in the monadology, Leibniz makes it very, very clear. He understands full well what the hard problem of consciousness is. So this is not new. This has been around for more than 300 years that we've understood this problem. So why have we not made any progress? I think the reason is very simple. We've made a fundamental mistake. We've assumed that space-time is fundamental. And it's not. Space-time is doomed. In our best theories, namely evolution by natural selection, general relativity, and quantum field theory, all three pillars of modern science are telling us that space-time is a useful framework, but it's not fundamental. There's a deeper, mathematically precise framework that we need to go for. It's not space-time. So the reason we've not made progress is we've assumed that objects in space and time exist when they're not perceived and that they have causal powers. That's the fundamental mistake. We've assumed that neural activity has causal powers. And it sounds crazy to say this, but I'm saying that neural activity, in fact, no objects in space and time have genuine causal powers. It's a useful fiction. And for everyday neuroscience, I talk about area V4 as causing color experiences and so forth. So that's the way I talk in everyday, but strictly speaking, that language is wrong. For everyday neuroscience is perfectly fine and I use it, but when we come to the hard problem, then that fiction comes back to bite us. It's very much like if you're, again, a wizard at a game like Grand Theft Auto, and you can talk about the steering wheel causing my car to turn left when I turn the steering wheel. And that kind of fiction is a very useful fiction, is harmless when you're playing the game. But if you're a software engineer and you need to do the next upgrade of the software for Grand Theft Auto, you have to get beyond that fiction. You cannot believe the fiction. If you're stuck in the fiction, you can't do the deep work that needs to be done to upgrade the software. And so that's what we're dealing with in the hard problem of consciousness. For everyday neuroscience, the fiction of neural causality is perfectly legitimate and fine. It's when we're having to get under the hood to actually deal with consciousness itself that fiction becomes the impediment to progress. So what I'm proposing then is that instead of starting with space-time and physical objects and booting up consciousness, why don't we try the other direction? So what we will go for is a mathematically precise theory of consciousness on its own terms, not as emergent, but a theory in which conscious experiences and what I call conscious agents are mathematically precise and are fundamental. So that's the approach. And then the idea then would be that objective reality, instead of being space and time, is a vast interacting network of conscious agents. Now, if we have time or during the Q&A, I can go into some of the details about the mathematics of conscious agents, and I've got a couple of papers that I can point you to. So we've published a mathematical definition of conscious agents and describe some of the circuits that we can create from conscious agents. But intuitively, a conscious agent has a set of possible conscious experiences and a Markovian kernel which describes the possible choices it can make based on those experiences. And networks of conscious agents then are going to be the fundamental object of study here. And one can prove straightforwardly that networks of conscious agents are computationally universal, so that anything that can be computed, for example, by deep neural networks can also be computed by conscious agent networks. So there's no problem with building networks that will do all sorts of things like learning, memory, problem solving, intelligence, and other interesting things that we would like to do. But the idea would be that consciousness is not being taken to emerge from an unconscious physical reality, but that we're giving a mathematical model of consciousness qua consciousness on its own terms. And now the burden is to go the other direction. we have to go from a dynamics of conscious agents, which is going to be network information theory. That's the mathematics that's going to be involved. It's very, very new mathematics, and many of the basic theorems of that whole area are yet to be proven. So it's pretty fun, pretty cutting edge mathematics, network information theory. But to go from the dynamics of conscious agents into space-time with a precise mapping. So the idea, just intuitively, why do we have space-time? Space-time is a visualization tool. So this network of conscious agents, think of it like the Twitterverse. The Twitterverse, there are literally tens of billions of users, billions of tweets, and there's no way that a Twitter user could interact with all the other Twitter users or read all the tweets. It's overwhelming. The social data there is just overwhelming. So if I want to understand what's happening in the realm of the Twitterverse, what do we do with overwhelming social data? What we do is we create visualization tools. We dumb things down. We take this overwhelming mass of data and we smash it down into some trivial interface. So we'd like to have some simple headset, a VR headset would be nice, with simple colored objects that move in certain ways, such that I can see, oh, well, what's trending in Amsterdam is such and such, and that's different from what's trending in New York, or I can zoom out and see what's going on in the United States versus what's happening in Europe. So we have visualization tools which make things simple and understandable. And that's what space-time and physical objects are. It's a particular data structure, a visualization tool that some conscious agents use to dumb down and understand this vast network of interacting conscious agents. So that sounds highfalutin and so forth, and perhaps a little crazy. What's the beef? How we're going to actually show that there's some beef here? The idea would be to show precisely how space-time arises as a visualization tool, to get a mathematically precise mapping from a network dynamics into space-time. And that's what my team and I are working on right now, is that mathematical mapping. And so this is the mapping we're working on. So here's the vast network of conscious agents, network information theory. We have to have, this arrow has to be mathematics, and that gives us back space-time. So we have to get evolution by natural selection. We have to get general relativity. We have to get quantum field theory as projections of a more general dynamics of conscious agents. If we can't do that, we're wrong. So there's a clean path toward a clean target. If we cannot get from the dynamics of conscious agents to get generalizations of evolution by natural selection, gravity, and quantum field theory in space-time, then we're wrong. So all the work that we've been doing inside space-time is going to be a boundary condition on a deeper theory of the dynamics of conscious agents. So one way of thinking about it is that science, for the last 400 years, has been studying our headset. And we've sharpened our tools. We've really gotten good scientific tools for the first time by studying our headset. And now we're ready to go backwards outside the headset and use those tools to explore the realm of conscious agents. And we'll know if we're on track by whatever mathematical model of conscious agents we get out here. That dynamics has to look like evolution by natural selection. It has to look at a different scale as the standard model of physics. If we can't get that kind of mapping, then we're wrong. So there's going to be a strong boundary condition on what we're doing here. And I'll just say at top level, the connection that we're looking at is the asymptotic dynamics of the network of conscious agents can be captured, one can prove, by things called affine permutations. Ultimately, the asymptotic dynamics is doubly stochastic Markovian kernels, and the extreme points of those are permutation. We're using affine permutations, and it turns out that these affine permutations are the deepest structure that the physicists like Nima Orkani Hamed are finding behind space-time So the physicists are using space-time and using mathematics as the flashlight into the dark behind space-time. So they're trying to, what's behind, what could possibly be behind space-time, right? That's a really, really hard problem for a physicist because, you know, what are you going to put out there behind space-time? So all they can do is try to just posit mathematical structures and then see if those structures can give you back quantum field theory and gravity and so forth. And the deepest structure they're finding, even behind the amplituhedron, are these affine permutations. Well, it turns out that permutations are the right way to data compress the dynamics of these conscious agents. That's a good way of compressing by looking at the asymptotic behavior. Instead of the step-by-step behavior, you only look at the asymptotic behavior, the trending. Like in the case of the Twitterverse, you're looking at just the trends, not each individual tweet. So when you look at the trends instead of each individual tweet, you're getting these affine permutations, and it turns out affine permutations are right behind the structure that the physicists are finding. So when you look at your face in a mirror, you know firsthand that what you're really seeing is trivial. What you literally see is trivial compared to the rich world of conscious experiences that lies behind what you're seeing. And so I'm proposing that we need to recognize that what we have taken as fundamental reality, namely the physical world, is not the fundamental reality. It's merely a data structure. And it's time for us to reverse engineer that data structure and find out what's behind it and how that projects into our data structure and to understand what's going on. And with that, I'll just close by saying one interesting question is artificial intelligence. Does this approach have anything to say about could AIs be conscious? And I think the answer is yes, but in a very, very different way than is standardly thought. The standard way is, as I mentioned earlier, is to say, yes, AIs can be conscious because any machine, machines can be conscious. The brain is a carbon-based machine, and it can be conscious. So surely once we figure that out, we'll be able to make silicon-based machines. So consciousness can emerge from a pre-existing physical system. I'm saying that whole approach can't be right because no physical objects have any causal powers. Space-time is doomed. So that whole approach is conceptually misguided. But there is a different way of thinking about it. When we go back here, your face is a portal. When I look at someone's face, I don't see their consciousness directly, but if someone's smiling, I can tell that they're happy, probabilistically. If they're crying, I can say something about their conscious state, that they're probably sad. So it's a fallible but genuine portal. So our interface gives us portals into consciousness. In the case of the cat, my portal is not as good. In the case of the mouse, it's dim. In the case of the rock, my portal has given up. But it's not because I'm not interacting with consciousness. It's because my interface necessarily has to give up. That's the point of an interface, is to dumb things down. So when I see a rock, I'm not saying that rocks are conscious. I'm saying that my icons are so simple at this point that I'm not getting any information about the consciousnesses that I'm interacting that are beyond space-time. So this is not panpsychism that I'm proposing here. So the idea would be this. Once we have this model, this network information theoretic model of conscious agents, it's mapping into space-time, then we should be able to reverse engineer our interface and open up new portals into the realm of conscious agents. That technology may look like circuits and software. It may look like standard AI, but it will be a different framework. We're not creating consciousness from unconscious physical ingredients. We're opening new portals into this pre-existing realm of conscious agents. So with that, that's probably crazy enough. I'll stop with that and just give thanks to many of my collaborators on this and open it up for questions.
Thank you very much, Donald. Yes, dear colleagues, I think that if you find this seminar mind-blowing, well, that's correct, it is, I guess, and that's the intention of Donald, I understand. I see already, and Maria will moderate the question, that some of our colleagues, including people who are knowledgeable about the string theory, for example, that you mentioned, have question for you. I will start with a very basic one, one of those very old philosophical questions. Is self-consciousness at the same level of consciousness or a prerequisite? When you say, when you look at you in the mirror, when you steer the wheel, when you recognize, like or otherwise, chocolate, is this I, me, a prerequisite to recognize the chocolate, steer the wheel, look at the mirror, or it's in the same category of anything else?
Great question. And that raises an important issue, which is when you're trying to boot up a theory of consciousness, a mathematical theory of consciousness, what do you do? How do you make such a theory? There's tons of things that you want the theory of consciousness to do: learning, memory, problem solving, intelligence, the self, conscious experiences, free will. The list goes on and on. And if you just throw the kitchen sink into your definition of consciousness, then that's not what we want. What we want is what Turing did when he was getting a theory of computation, right? Computation is a wild and woolly field. There's the traveling salesman problem, computing pi. There's lots of things that goes on in computation. What Turing did was to give us the idea that this trivial device that we call a Turing machine, a small set of states, start state, halt state, transition rules, and a tape. That trivial formalism, he claimed, captures everything about computation. Anything that can be computed with what we call a Turing machine. And so that's what we need to do, is to find, for theory of consciousness, what is the minimal set of assumptions that we can make that would boot up a theory capable of handling everything that we want to say about consciousness. So what we've done is we've chosen two things in our mathematical model, and we'll see, the proof will be in how well it works. We've chosen to define a conscious agent as a formal system that has a set of possible conscious experiences, like a headache, smell of vanilla, whatever, and a Markovian kernel, which for each conscious experience tells you what actions that agent will take to affect the experiences of other agents. So experiences and a Markovian kernel for actions. And then you have a network of these. So that's it. There's no, by the way, you can see I haven't assumed a self. There's no explicit notion of memory or learning, problem solving, intelligence. All those things have to be created as emergent from networks of conscious agents. And the one thing that comes out of this is that when agents interact, their dynamics actually satisfies the definition of a conscious agent, and so new agents emerge. So this is a scale-free model of consciousness, which is really quite interesting. So the answer to your question now is there is no self in the fundamental definition of conscious agents. We have to actually do the hard work of building up a self. And my own guess is that we're going to see that you use part of some conscious agents working together in networks will create higher level agents that use some of their experiences as what they call me, as a way of again, it's a user interface description of understanding your own actions. See, my body itself, when I look at my body, it's just an icon. It's not the truth. I actually don't see myself as I am. I'm seeing myself through a description. My body is merely an icon. I don't actually know what I'm doing. When I pick up a pencil, I don't know what I'm doing in reality. All I know is what I'm doing under a description in my interface. So everything about me is a representation, including my psychological sense of a self. So the self, even down to my body, is going to merely be a data structure. In the case of death, then, it may be that data structure, consciousness may continue, but I have to do the math. I don't know what will happen to those data structures. Do they get preserved, or do they dissolve and new structures emerge? So you can see it changes the whole framework of thinking about this thing.
Thank you very much, Donald. It reminds me of some Buddhist philosophy, by the way, about the self doesn't exist as part of a network, but without the mathematics that you're definitely putting into that. But I leave to Maria now to moderate the very interesting questions that are coming from the chat.
So I'd like to start with a set of 3 questions that are coming from a physicist, Wieland. So he's asking, which role does quantum entanglement and superposition take in the reductionist view of conscious reality? Are there other theories other than Hameroff-Penrose?
So it turns out that it's quite remarkable that quantum theory, quantum information theory, is really just the algebraic structure of space-time. That's remarkable. For those who are interested, I suggest a book. It's called Geometric Algebra for Physicists, and by Duran and Lassenby. And what you see there is that space-time has an algebraic structure. It's a geometric algebra of signature 1, 3 for Minkowski space. And it turns out that the algebraic properties of that space-time, that the Dirac matrices are simply matrix representations of that algebra, and that the Pauli matrices that are at the foundation of a lot of quantum information theory are merely matrix representations of the so-called bivectors of that algebra. And so the idea that space-time is one thing and then quantum theory is something else that we have to put together, it turns out that's not deep enough. It's that when you look at space-time itself and its algebraic structure, quantum information theory actually emerges as the algebraic structure of space-time. And so from my point of view, what we'll be seeing here, and the reason I've gotten into this, I'm a cognitive scientist, I'm not a quantum information theorist, but so the reason I've been studying this is because, as I've told you, my project now is to show that space-time is just a data structure. It's a visualization tool. So I've had to start to learn about that data structure. And so what's remarkable is that entanglement and quantum information theory are all going to be properties of our particular data structure. They're not, what it means is that the deeper reality beyond space-time is not quantum. So a lot of people say, if I'm looking for a reality beyond space-time, maybe quantum entanglement may be the deeper structure. Well, it turns out that quantum entanglement is a property of the algebra of space-time itself. So when Nima Arkani-Hamed and these other physicists are finding structures behind space-time, there are no Hilbert spaces there. These structures have no Hilbert spaces and therefore no notion of entanglement. So this is a truly, I mean, there's been some interesting work by quantum physicists trying to use entanglement to build up space-time, but what Nima's doing is even more profound. It's saying, I'm going to a place where there are no Hilbert spaces, so there's no entanglement. So that's the direction that I'm pursuing, that quantum information theory is merely the algebra of our user interface, space-time.
Okay, and then another question from our same colleague. The representation of scattering amplitudes through Feynman diagrams is a highly perturbative approach, whereas protons and neutrons only exist through highly non-perturbative interactions. Do you have any thoughts on non-perturbative origins of conscious realism?
Well, so the idea would not be that consciousness emerges somehow non-perturbatively. The idea is that consciousness is fundamental. So I'm going the other direction. So I'm starting with a dynamics of consciousness, and I have to show how the scattering amplitudes come out of it. So now, of course, I'm not an expert in scattering amplitudes, so I can just tell you what the physicists like Nima Arkani-Hamed are doing. What they're finding are formulas for scattering amplitudes where the scattering is actually the volume of a polytope in high dimensional space, like the amplituhedron or the spacehedron. And so now the technical work that they're doing, the first work that they did was for what they call tree level amplitudes. But now they're getting amplitudes for loops, multiple loops and so forth. So they're starting to look at the perturbation theory kinds of notions, but they're getting it from a non-perturbative kind of approach. So instead of, see the problem with the Feynman diagrams, according to, again, but I'm telling you as a cognitive scientist who's reading the physicist's work, but if you want to hear the real thing, go look up Nima Arkani Hamed and his papers on that. But at top level, what Nima will tell you is that the Feynman diagrams are enforcing locality and unitarity. So they're making you do everything within the data structure of space-time. And so that you have to make all these virtual particles and more and more virtual particles. And that's why you get these hundreds of pages of algebra when you're trying to get 2 gluons in and 5 gluons going out. So, but when you let go of space-time and you let go of virtual particles, so Nima and his approach, there are no virtual particles anywhere. They'll say everything is on shell. There are no virtual particles, and that's the power of their approach. When you let go of space-time, and you let go of Hilbert spaces, then you find these deeper structures that just show you the deeper symmetries in the data that are hidden by space-time. So, and that's no surprise, right? If I asked you, given the geometry of the desktop on your computer, tell me what's going on in terms of the circuits and software inside your computer. Well, good luck. That's the wrong language. Pixels on your desktop is just the wrong language to actually get a deep understanding of the circuits and software. And that's what the physicists seem to be finding. I mean, Feynman is stuck in space and time, locality and unitarity, and that's just the wrong language to describe what's going on deeper, and it's missing the symmetries. So that's sort of, but of course, that's a cognitive scientist. I would go to Nima directly.
Another question from our colleague, Xavier Zawi. If space and time is doomed, will cause and effect be as well?
That's a deep philosophical question. My own take right now, of course, physical causality is doomed, right? But what about causality in consciousness? There, I'm de facto using a mathematical model that I interpret as at least probabilistic causality. So the Markovian kernel, right, for each conscious experience that an agent has, there are probability measures for the kinds of actions it might take. Now, the way I can just keep the mathematics and just use the mathematics as it is, but of course I want to try to have an intuitive understanding of what that might mean. And the way I think about it right now intuitively is like a probabilistic notion of free will. But if that's the way, then free will in this probabilistic notion is a fundamental cause in this theory. And I'm sort of going that direction because if I interpret probabilities as objective chance instead of free choices, so that means when I have probability, I can think of it as free will choices or just objective chance. Well, objective chance now would, if I did that, if I went that way, I would be a dualist. I would be saying, in addition to this realm of consciousness, conscious agents, there's this unconscious realm, objective chance, that's also funneling new stuff into reality. So I would be a dualist. So I don't want to be, I would like to have a monistic theory. So the way I'm thinking about it right now is, in this realm of conscious agents, conscious experiences inform free choices. So there's a notion of inform that has to be unpacked, that I have to understand. The conscious experiences inform free choices, and free choices are the only causes. And the notion of free will that comes out of this is really quite interesting, because when agents interact, they create new agents with a new level of choice. And so the model of free will that's coming out of this is not at one level. It's going to be very complicated. It'll be both bottom up and top down choices in this big network of conscious agents. And that will be the notion of causality that comes out of this. And the reason we get what looks like physical causality is because what we're doing is we're collapsing this whole huge, complicated free will choice dynamics of conscious agents into a space-time interface, into things like rocks that are falling off cliffs and accelerating, under gravity. So we get the feeling of causality in space and time as a really dumbed down user interface description of this really complicated top-down and bottom-up dynamics of free will that I'm looking forward to explore mathematically. It's going to be incredibly complicated, but that's going to be the idea.
So our colleague Tongi is asking, so does that mean we're living in the matrix?
Interesting. At first level, I would say yes. Okay, yes, but at a deeper level, I'll say this: that of course in the Matrix, when Neo takes off, gets pulled out, the thing out of his neck, he's back into a space-time reality. So the reality outside the Matrix is still space and time. So what I'm saying is more radical, right? That's the space-time itself is just our headset, and when you unplug from that, it's unlike anything inside space and time. The very language of space and time is the wrong language to describe this deeper reality. So in that sense, it's not like the Matrix, and also it's not like simulation theory, right? So Elon Musk and Nick Bostrom and so forth have the simulation idea. And so again, at first blush, it's similar, right? So what I'm saying is similar, but let me say where it's different. In the simulation hypothesis, right, there's some programmer that may be programming us. But then there's a deeper level where there's a deeper level of program that's programming that programmer, and all the way down until you get to some base level. Well, in the standard simulation theory that Bostrom and others think about, that base level is still a physicalist space-time. So there's some physical programmer in some space-time at the bottom level. And so I disagree there. I'm saying that the fundamental level is outside space-time. This is the biggest step we have to take. We literally have to let go of our headset. It's so hard to let go of our headset. We've been living our entire lives in our headset, and science has only studied our headset. That's all we know. It's huge to step. It's just like Neo taking, the first step out of the Matrix. It's very, very difficult. But the second thing that's different from my point of view than the simulation theory is not only that the base level is not physical, but also that the simulation theory assumes that unconscious circuits and software can create consciousness at the next level. Well, that's the hard problem of consciousness, and that's the very problem we can't solve. And that's the very problem that's forced me to step back and go, what's wrong here? And to say we have to let go of space-time. So simulation theory assumes, well, I'll put it this way: the simulation theory itself must have a solution to the hard problem for us to take the simulation theory as a genuine theory. And they don't have a theory of the hard problem. We don't know how consciousness can be booted up from circuits and software.
So I have a question from our colleague Jonas, and he was asking, is your theory related to the idea of God? And if so, can God be expressed as a mathematical formula?
Well, I'm very interested now because, of course, when I take consciousness to be fundamental and space-time not, that's something that spiritual traditions have been saying for thousands of years, right? And so I've gotten a lot of contact with people from spiritual traditions who are interested in this. And my attitude about it is the word God, as it's been used by spiritual traditions, is not a technical term. It's not well defined. And I think that the language that we're developing now of conscious agents may allow us to propose technical terms so that we can actually start to do science in a realm that we never thought we could do science, namely what we call spirituality. So I'll be precise. For example, suppose it turns out when conscious agents interact, they form new conscious agents. What if it's a theorem, and I don't know yet, what if it's a theorem that there's one biggest conscious agent at any moment, right? The agents whatever the dynamics of agents is, there's always one biggest conscious agent. I could say that that's God. So that would be my technical definition. Again, I'm not saying that that's my belief. It's in the spirit of science to write down mathematical definitions and theories and then try to tear them apart. But at least we would, for the first time, we have the chance. So I'll put it this way. Here's a proposal. God is the biggest conscious agent. Conscious agent is a purely technical term. So I've just proposed, for the first time that I know of, the first mathematical definition of God. Now, of course, I'm wrong, but that's not the point. The point is to have a mathematically precise definition on the table so we can now begin the science process of figuring out why it's wrong. For example, maybe we'll find out that there is no such thing as it's not a lattice of agents, there's no top. Maybe there are multiple local tops. So maybe there's a polytheism. Who knows? What if this physicist named Giesen is right, and we should only be using countable numbers, but not the reals? Suppose that that's right. Then that will change what I think about the topology of conscious agents, and that will change what I would define as God. But the point is that not whether I'm right or wrong about my definition of God. I think the point is we now have mathematical tools where we can actually start to take what we thought of as spiritual ideas, make them mathematically precise, and start to do theorems and experiments. So science and spirituality can start to have a rapprochement after many, many centuries of being at each other's throats. If this approach is correct, if what the physicists are saying is correct, space-time is doomed. Well, the spiritual people have been there already for hundreds of years. They've already been saying that space-time is doomed, but they've not had the precise language to tell us what's behind. They have words and probably some very, very deep ideas, but we know as scientists that no matter how smart you are, deep ideas only go so far. You have to have mathematics. Like Einstein's deep idea, a falling elevator, you'd be weightless, right? That was his deep idea for gravity. It took him 7 or 8 years to turn that into an equation. And then the equation came back and told him things he didn't like and didn't believe, like there are black holes and the universe is either expanding or contracting. That's the whole point of taking our ideas and making them precise. So I want to see that in the realm of spiritual ideas. And what comes out of it may be very uncomfortable for people in spiritual traditions because science is not dogmatic. We have to go wherever the math and the experiments and the data take us. And so it may be an uncomfortable journey for many people in spiritual traditions to have their ideas made precise and then disproven, or versions of them disproven as we move to deeper ideas. So we'll see.
So now I have a couple. So 2 colleagues have asked a very similar question, Diana and Michelle. One is saying, without having experienced the world, does a baby have consciousness, or does a fetus have consciousness? And when does consciousness emerge in a human being? And again, our colleague Michelle, at what age does a child develop self-consciousness and how? Maybe I'd like to add just a little bit of an extra part on this question. Are you saying that consciousness can exist in the absence of life?
Oh, great. So a bunch of good questions. The distinction between living and non-living from this framework is not an insight into a deep distinction in reality. It's an artifact of limitations of our interface. Right? So this whole framework makes a very, very clean proposal. There is, in reality, no fundamental distinction between living and non-living. There's just our interface gives us more insight and less insight. We're always interacting with conscious agents. That's the framework. So we're always interacting with consciousnesses. But when my interface gives me back a symbol that I call a rock or a proton, my insight into consciousness is there's none. But when my interface gives me back a symbol that I call a human face, my interface is giving me a symbol that allows me to have some insight into the consciousness that I'm interacting with. So this makes a non-trivial prediction that one reason why we've been having a hard time defining life is because there is no principal distinction between living and non-living. So, and then the notion of, when does consciousness emerge in development, and the notion of a self. Well, once again, the framework in which I'm trying to answer these kinds of questions is not the physicalist framework in which, the child is born and it has, neurons which now have to form, the right kinds of synapses, and then prune those synapses and so forth. And at some point, consciousness emerges, and so forth. In other words, the physicalist bottom-up framework, the reductionist framework, is not the framework I'm thinking about. So consciousness itself, when conscious agents interact, they create new conscious agents. And the new conscious agents then have to, in some sense, learn and make their own interfaces. So the notion of a self is going to be, as a new conscious agent emerges, it's creating its own interface. It's taking some of its experiences, and by acting and looking at the experiences, it builds its own interface description of itself and of what it calls the other. And so this, as you can see, this way of thinking, it's utterly alien from everything that we've been raised in, right? Letting go of space-time and neuroreductionism is not easy. You have to rethink every problem from the get-go. So it's a very, very different way of thinking about things. I hope that helps.
So we have another question from our colleague Yasmin. She says, does studying the brain help to understand consciousness at all, in your view?
Absolutely. And in fact, when I say that space-time is doomed, and that, we need something beyond gravity and quantum field theory and evolution by natural selection, these are incredibly powerful theories. And neuroscience is an incredibly powerful tool. And in fact, what I'm proposing here is job security for neuroscience, right? We thought that if I look inside of a skull and I see neurons and synapses and ion flows, that's the reality, and that's what I have to deal with. Now I'm saying we have to reverse engineer that. When we look inside the brain and we see neurons and systems and axons and ion flows, we have to reverse engineer that. But that's just an interface description of a much deeper reality. So we have to have the network information science knowledge of conscious agent dynamics, project that mathematical dynamics into space-time, find the part of it that looks like brains and neurons, and then reverse engineer. So when I see what I call a neuron or a synapse, pull that back into the network of conscious agents and ask, what is really going on in the realm of conscious agents that I perceive as a neuron or a synapse or a system of neurons? So we're going to have rules for reverse engineering our interface. So neuroscience is going to be far more difficult. We can't just take neurons and ions and synapses at face value. We're going to have sophisticated interpretations of these things in terms of their pullbacks into the network of conscious agents. So there's tons of interesting work there. And that's going to be true of all of the sciences. It's very much like someone who's only played Grand Theft Auto all their lives, and we're wizards of Grand Theft Auto. And we learn for the first time that the steering wheel corresponds to some kind of control system in a computer that you didn't even know existed. And you have to reverse engineer what you thought was the steering wheel and ask, what is it in the supercomputer software that corresponds to the steering wheel, and what corresponds to the gas, and what corresponds to the dashboard, what corresponds to the other Ferrari. So in other words, we really have only studied our headset, and we've never studied objective reality. We're going to be taking our first steps outside of the headset into objective reality, and we're going to have a lot of work to do to understand how to do that.
So we have a question from a colleague, Giacomo. He says, how do you plan to remove your interface in order to study the conscious agents without the distorting filters?
Well, some people, after hearing these theories, say that I must have been removing the filters by doing a lot of drugs already. The only way I think that to go on this is the scientific method, right? So we simply propose mathematically precise theories. We look at their consequences and we test the consequences. It's possible that we don't have the concepts needed to get a theory of reality beyond space-time. I don't know. I can't rule that out. I mean, I don't expect monkeys to understand quantum mechanics. It's quite possible that we don't understand what we need to understand to go outside of our headset. But the approach I'm taking is to say, I don't know what ultimate reality is, but what I can do is propose a model of reality that in which it's self-consistent in the sense that it explains why I'm able to understand that reality. I am a conscious agent. So the reason why a theory of conscious agents can be understood by me is because I'm not divorced from that reality of conscious agents. I myself am a conscious agent, in fact, multiple, countless conscious agents. And so I think our approach here has to be the scientific method. And ultimately, every scientific theory has assumptions that it makes. No scientific theory explains everything. The assumptions are where that theory stops. A deeper theory might make new assumptions that are deeper, but that can explain the old assumptions. But science can never get to the bottom. I don't think there can ever be a theory of everything, because every scientific theory must necessarily start with assumptions. And so science will, I think, be endlessly going for deeper and deeper theories with deeper and deeper assumptions. And hopefully maybe conscious agents is just the next step.
I'd like to go back to a question that was posed near the beginning that I haven't asked yet from Michelle, which is, what new light can your research shed on the meaning interpretation of Shakespeare's sentence, thus conscience does make cowards of us all, whereby I should say this is conscience spelt conscience rather than the conscious. And then maybe for me, do you see a relation actually between those two words?
Conscience in terms of like the moral.
Conscience in terms of, yes, I did something bad, I feel guilty because I have a bad conscience.
Right. Well, on that moral side of things, the feeling bad and feeling guilty and so forth, right? The only scientific framework we have right now that cuts the mustard on that is evolutionary psychology, right? So evolutionary psychology is the only scientific field that really uses deep explanatory principles to actually predict and understand the complexity of human emotions and how they evolved. And it's a beautiful theory. But ultimately, we're going to have to go deeper, right? If this theory of conscious agents is correct, we're going to have to understand evolutionary psychology as a special case of a deeper theory of conscious agents and their interactions. And so one direction I'm thinking about on that is, evolution only occurs when there is competition for limited resources. It's the limitation of resources that is absolutely essential for evolution. And evolutionary psychology then gives a theory of, for example, guilt, in terms of, for example, we're a social species, that we have to cooperate, we hunt and gather, and I go out there and hunt and share and so forth, but I could cheat and not hunt, and I could just sit around and be lazy and ask you to give me some of yours. And so evolutionary psychology then gives a theory about how we evolved emotions of of anger for cheaters, because if people cheat, the whole species could collapse, right? If everybody's a cheater, no one eats and we all collapse. So evolutionary psychology gives this very, very beautiful theory about the origin and evolution of anger, guilt, social pressure, and so forth. Also the need for revenge. but it all comes in a framework that assumes limited resources. I don't know in this realm of conscious agents if it's going to be true that there are limited resources. And so it may be, and this is going to be fun to explore, it may be that our evolutionary psychology is an artifact of the illusion of limited resources because we're wearing a headset. And the headset is data compressing a far richer reality into a much less rich reality and giving us the illusion of limited resources. So in that case, then it may be that these kinds of, the conscience and emotions are artifacts of the limits of our headset and may not be an indication of this deeper reality. It remains to be seen. Maybe there will be a theory of conscious agents in which we do have limits. So I'll be very interested to see where that goes. But now in terms of Shakespeare, I don't know. I think the one thing I would say about the cowards aspect of it is, I mean, there's a question that is an obvious one to raise to this whole framework that I'm talking about here, and that is that if consciousness is fundamental, what is it doing and why? Right? Why isn't just consciousness just sitting there fat, dumb, and happy? Why is consciousness doing anything at all? And the answer is I don't know. But the only idea that I've run across that's deep enough to be a possible answer to this question is from Gödel's incompleteness theorem. And Gödel, just in brief, what his incompleteness theorems show is that there's no end to the exploration of mathematical structure. No matter how much mathematical structure we have discovered or invented, we've only begun. And the reason this is interesting here is that in the case of conscious realism, where consciousness and conscious agents are the only thing that there is in this metaphysics, then mathematics and mathematical structure in that framework is all and only about consciousness and conscious agents. In which case, what Gödel's incompleteness theorem is telling us is that there's no end to the exploration of the varieties of conscious experience. So I call this Gödel's candy store. There's this infinite candy store, or if not infinite, boundless candy store of possible varieties of conscious agents and conscious experiences. And in principle, the exploration of it can never end. And in principle, consciousness can never, ever do anything but just have gotten started exploring. And so what consciousness is about is the endless exploration of its own possibilities. Now to the coward part. And I had to say all that just to get to the coward part. What does exploration involve? Well, exploring new possibilities sounds exhilarating, but it's also terrifying, because to really go into something profoundly new, you have to let go of something that you know and feel comfortable with. So exploration has this bit of first letting go of what you already know and going into a new realm and getting a whole new set of concepts and so forth. And so that may be fundamental to the whole dynamic of consciousness. There may be this exhilaration and cowardice at the same time at every step of the way, but that's part of the necessary evolution of consciousness and exploring the candy store. It's not all fun and games. It's an adventure that's like a roller coaster. It's scary. What's around the next turn? So that's my non-literary interpretation of Shakespeare.
So maybe we'll go for a final question from Xavier again. You mentioned emerging conscious agents formed by the aggregation of several ones, but do you also consider the opposite, i.e. new conscious agents emerging from the subdivision of a single one?
We haven't, and that's an interesting idea.
So that was
I myself don't feel like I'm an expert in my own theory. We're at the very baby beginning, and I could easily see someone who is an expert in network information theory reading my paper and in 2 weeks being miles ahead of me on the development of this network of conscious agents. So I would say I would love to have people leave me in the dust on this. People who know network information science can just read my paper, see the limits and the strengths, and run with it. I would just love to read your papers on this. So if someone can come up with a model of conscious agents in which it's not only agents combined to create new agents, but somehow there's a subdivision, I'm all eager, because I absolutely am not, I'm learning network information theory. Like I'm learning physics, I'm learning scattering. I mean, there's just so much to learn when you're trying to, change your framework like this. So I'm eager to have experts run ahead of me on this. So I hope you're right.
Maybe then I could ask one very final question. Sorry, it came in from a colleague, Tatiana. So she's asking, when there were breakthroughs in other theories like Einstein's relativity, there were ways to prove it or to test it. Is there a way, I mean, that you can be sure about whether your theory is true?
Well, my focus right now is to try to answer that question. And the direction I'm going is, so this is exactly what I'm working on. I'm trying to show that the asymptotic behavior of the dynamics of conscious agents is captured by these affine permutations. Those affine permutations are the deepest structure underlying the amplituhedron and the associahedron that Nima Arkani Hamed and the physicists are finding behind spacetime. They have found the mapping from the amplituhedron into spacetime and scattering amplitudes. And so what I'm trying to do is pull a thread all the way from the dynamics of conscious agents through its asymptotics into affine permutations, from affine permutations into the amplituhedron and spacehedron. And from there, the physicists can take me all the way into spacetime. So in other words, for me to have empirical tests, I have to start with conscious agent dynamics and make predictions in spacetime. And so that's why this is my full occupation, is to get the map all the way into spacetime. I think Nima's work is the best hope I've got to do that. And then I've got to reverse engineer. I've got to say, okay, what does a particle in spacetime, a scattering of it in spacetime, mean in terms of conscious agent dynamics? And then I can start to make empirical predictions. So that's my goal, is to make empirical predictions, but you can see it's not going to happen this weekend.
So we'd like to thank you very, very much for this seminar, and I'm going to hand over to Angela to say the final words.
Well, I think that clearly there cannot be final words on a subject like the one that we have been approaching this afternoon in Brussels, morning in California, but of course time and space doesn't exist, so we are in the same dimension in our virtual space, right?
Right.
I think this is what happens to all thinkers who are thinking beyond what we can experience, right? So this is what another physicist is saying, Carlo Rovelli, and he's telling us, well, in our own experience, time and space does exist. And in our experience, it does make a difference, which of course doesn't mean that, as you say, it can be an icon on the screen, and we should not confuse the icon and what is behind it. But I think that I express surely the thinking of all our colleagues in thanking you very much for being with us, for definitely providing a lot of food for thought and challenging assumptions, disciplinary and other boundaries, even the boundaries between spirituality and science, and whether science is mainly about mathematics that people like philosophers might challenge you a little bit about, yes. Or others. So I hope we also provided you with further food for thought. I really appreciated your openness about read my paper if you have something to say. If you bin this in 2 weeks and take it further, I will be very happy. As you said, one of the big differences between some, at least, forms of spirituality and science is that science is not dogmatic, as you say. And this is the beauty of, I think, our work. We are very privileged to work in a field where we can challenge any assumption with all the methods we can find, have robust discussions, and try to understand what something is according to our best possible understanding, and move forward until we find a better question or a better answer to the question or a better way to try to link the two. So I think this has been really very exciting and very interesting. So thanks for waking up very early in your experience in California to be with us in Brussels. And I'm very happy that we moved from the good surrealist option of this is not a seminar and we have no speaker into we had a wonderful seminar with a brilliant speaker. Thank you again.
Thank you so much. It was a great pleasure.
Thank you.